In this video, we're going to talk about differentiability and how a function might fail to have a derivative at a particular x value. So first, I just want to remind you of a definition you should know at this point. That is that a function is continuous at x equals a if the limit of f of x as x goes to a is equal to f of a. So the definition of continuity relies on a limit existing, namely the limit as x approaches a of f of x. And so similarly, the definition of differentiability relies on the limit, except that it's the limit of the slopes of the secant lines that can be drawn. And if you look here below, I've got the two limits that need to be equal to each other in order for a function to be differentiable. So this is the difference quotient. You can see the slope in there, right? It's just two y values divided by the difference between two y values over the difference between two x values. But in any case, a function won't be differentiable if these two limits are not the same, if the right hand and the left hand limits of the difference quotient are not the same. So now we're just going to go look at a few different cases that will be obvious visually, but we're going to just use this definition to back it up theoretically. All right, so take a look at the function f of x equals the absolute value of x. Graphically, we can see that at x equals 0, right, something interesting is happening. It looks like the function changes direction very suddenly. And so the question would be, is f of x differentiable at x equals 0? To justify that with our definition, we're going to look at the limit as x approaches 0 from the right of f of x minus f of 0 divided by x minus 0. But of course, f of x is just absolute value of x, so this ends up being the limit as x goes to 0 of absolute value of x. And f of 0 would be the absolute value of 0, so that's just 0. And then x minus 0 is just x, so you end up getting this. And then so I haven't finished evaluating that. We'll come back to that in a second. If you come from the left-hand side, it would be the same thing. So I don't need to rewrite it again. I mean, I'll start it, but oops. So same definition, it's just we're approaching from the left-hand side. And this is going to equal same thing, but of course leaving out a few things here. Same thing, but as x approaches 0 from the left. So how do we actually evaluate these limits? Well, we can't plug in 0. One thing you could do is to notice that when you're approaching 0 from the right-hand side, the absolute value of x graph is really just the same as x, right? Here's the right-hand side of the absolute value graph, and that is just the same as the function x. So it's the limit as x goes to 0 from the right of x over x, but that's just 1. And similarly, if you approach from the left-hand side, the absolute value of x function is just behaving like the graph negative x. So this is just the limit as x goes to 0 from the left of negative x over x, and that gives me negative 1. All right, and so those are not the same. So the answer to this would be no. Right? Those two limits are not the same. You can understand this more visually by just noting that at x equals 0, if we were to sort of plant our x value there at 0, and then start considering the secant lines you can draw. So here's 0. And let's just start drawing secant lines. So there's a secant line. What's the slope of that secant line? Well, it's 1. And even if I keep moving that second point closer and closer, the slopes of those secant lines are always going to be 1, right? And on the other hand, if I come from the left-hand side, and again, I'm planting my point there at 0, and I draw this secant line, well, the slope is going to be -1, and it's always going to be -1, even as I move that point closer and closer. So visually, we can see that the right-hand limit and the left-hand limit are not equal, and we can tell that the slopes are 1 from the right-hand side and -1 from the left-hand side. But to be rigorous, the evaluation of the limits below would actually show you that. Let's do one more example. All right, so yet another example. This time we have f of x equals x to the 2/3. So we ask the same question, is f of x differentiable at x equals 0? Well, this time let's start with the actual visual, let's actually start with the visual analysis. I'm going to plant my point there at 0, and I'm going to put another point there. Now, I can draw a secant line, and the question is, what's happening to the slope of that secant line as I start moving the point closer and closer? It's kind of tough to tell, but ultimately these lines, I'm going to draw them over here, these secant lines are going to start looking more and more vertical. And that means that their slopes are approaching infinity. So I'm going to say that the slope from the left-hand side is, I guess we won't say equals infinity, I'm going to say going towards infinity. And on the other hand, if you come from the other side, then there's a secant line, and as you start drawing more and more secant lines by moving that point closer, you're going to get slopes that look like this. So more and more steep, and that means that more and more steep but still negative, so those slopes are approaching negative infinity. So the result is that we got what's called a cusp there, and a function will not be differentiable where it has a cusp. And we're going to take a look now one more time at those difference quotients just to justify this. If I look at the limit as x goes to 0 from the right of f of x minus f of 0 over x minus 0, well, that's just going to be x to the 2/3 minus f of 0 would be 0, and then divided by x minus 0, that's just x, and this is the limit as x goes to 0 from the right. Let's just use a property of exponents here. I'm going to call this x to the 2/3 divided by x to the 3/3, and when you subtract exponents, you end up getting x to the -1/3, which is the same as 1 over the cube root of x. And if we do it from the left-hand side, we'll get the same thing, but we're considering the limit from the left-hand side. So we end up getting this. So how would we analyze these? Well, for the top one, we'd have to plug in numbers really close to 0 on the positive side. So if you imagine taking the cube root of really tiny positive numbers, you're going to get really tiny numbers. But then those are in the denominator, and 1 divided by a really tiny number is just infinity. And on the other hand, if you plug in numbers that are really close to 0 on the left-hand side, then you're taking the cube root of really tiny negative numbers, which results in really tiny negative numbers, and since those are in the denominator, you've got 1 over a really tiny negative number, which in the long run goes to infinity, negative infinity. And those are not the same. So the limit does not, those limits are not the same, and so the function is not differentiable at x equals 0. We'll finish the next two examples by just doing it visually, because I think those two examples should serve as the idea. You're going to end up just, this is just to justify what we all know, which is that functions are not differentiable at corners and cusps. The two next examples are a little bit different, so let's look at those. So here I've got the cube root of x, and we ask the same question. And this time we're not going to do it rigorously. We're just going to kind of draw those secant lines. So here I'll plant a point, and we consider the slope of that secant line. We consider the slope of that secant line. And as we keep moving that point closer and closer, hopefully you can see that the slope's approaching infinity. Similarly, if we come from this side, we can see that those slopes are getting closer and closer to infinity as well. So you might think that, oh well, it must be differentiable, but since those limits are approaching infinity, and infinity is not a definitive value, we have to say that this function is also not differentiable at x equals 0. So what ends up happening is you're drawing a vertical tangent here. If you draw a tangent line there, it's a vertical one. Anytime you have a vertical tangent, we also state that the derivative does not exist at that point. Even though there's smoothness here, right? The curve is smoothly changing, but that instance of a vertical tangent where the slope is infinity, since infinity is not a number, we're going to say that it's not differentiable. So vertical tangents are out. And for the last example, we'll see that a function also needs to be continuous. So f of x equals the absolute value of x over x. I changed it a little bit just because that function has no value at 0, so I changed it subtly just so we can actually consider there being a point here. So I'm going to kind of darken that. There is a point there, but there's no point here based on my new definition there. So let's just start drawing secant lines. Coming from the right-hand side, it's easy to see that even as you keep moving these points closer and closer, right, the slope is always 0. However, if you come from the left-hand side, right, whatever that slope is, it's less than that slope, which is less than that slope. And as we get closer and closer, you can see that the line's getting more and more vertical, so that slope's approaching infinity. And so therefore, if your function is not continuous, it has no shot at being differentiable. And that's because one side will probably end up going towards infinity, while the other sided limit is probably something completely different. So also not differentiable. And these are really all the cases I think you'll probably come across in this course. And they're again, visually you can tell when a graph is differentiable or not, but we wanted to kind of I wanted to connect the theory with those graphical representations. So that's differentiability. Now you know how to identify it, and you know the definition of differentiability. And so hopefully that can help you answer some questions that you come across.